Hello everybody. Thank you for joining this webinar. Topic of today's webinar is the structural design of long-span cable-stayed bridge with a case study of Balang Island Bridge. As we all know, bridges are usually representing how the human culture was developed. That's why the design of a bridge should merge various aspects of human needs and desires, so that should satisfy the following design criteria. The most important aspect is the structural safety and stability. However, other aspects should also be satisfied, such as serviceability, good construction method, economic, aesthetic, durable, easy for maintenance, as well as the environmental friendly. Moreover, for the long-span bridge, the engineer should take care of various design requirements. It doesn't only require to perform the traditional structural analysis, but it obliges to carefully consider also the specific site condition, so that a suitable construction method can be defined in optimal way of safety, cost, and timely manner. Now I want to introduce the Balang Island Bridge. Indonesia is an archipelago consisting of more than 17,000 islands. Among the provinces, East Kalimantan is one of the developing provinces in infrastructures due to riches of natural resources. In this province, a long-span cable-stayed bridge is being in construction in the area of Balikpapan Bay, crossing Balang Island near to the city of Balikpapan, one of the biggest cities in Kalimantan Island. In fact, there are two bridges that will go through Balang Island, connecting the district of Tempadung and Penajam. The short-span one was designed as a multi-span concrete arch bridge, while the long-span one is a cable-stayed concrete bridge that will be our topic of today's webinar. The short-span Balang Island Bridge has three main spans of 105 meters each that is now finished construction, while the long-span Balang Island Bridge has main span of 402 meters, which is the longest span of concrete bridge in Indonesia. Because of such long span of concrete girder, an intermediate pier was designed in each side span for deformation control and stability reason. Connection between the pylon and the deck is proposed to be a longitudinal movable bearing, while the intermediate piers are connected to the bridge deck by 8 viscous dampers. Therefore, in case of a large horizontal force in longitudinal directions, such as seismic force, the pylon will receive only a small portion of force as a function of its self-weight, and most of the horizontal forces will be received by the intermediate piers through the viscous dampers. Meanwhile, the bridge is designed to still withstand even with the failure of the intermediate piers. This is the 3D view of Balang Island Bridge. Before the present design of cable-stayed bridge, in fact the Balang Island Bridge was designed previously as a suspension bridge with 810 meters span. But due to the collapse accident of other suspension bridge in the same province in November 2011, the local authority has decided to change the former design to a cable-stayed bridge. Beside of the above reason, in fact, the cost comparison shows also that the cable-stayed bridge is around 30% cheaper than the previous suspension bridge design. Now we will talk about the structural modeling. For a long-span bridge, such as cable-stayed bridge or suspension bridge, the structural modeling should be in 3 dimensions so that the structural detailing can be well modeled. This is detailed modeling for pylon, longitudinal girders, transversal beams, and deck slab of Balang Island Bridge. We see more clear here the detailed modeling of longitudinal girders, cross beams, deck slab, and stay cables by using Midas Civil. This is the detailed modeling of deck girder and pylons connection by assigning the movable bearings. This is the detailed modeling of intermediate piers. We see more clear here the detailed modeling of deck girder and intermediate piers connection by assigning a viscoelastic model of viscous dampers. This is a detailed model of pylon on which the loop pre-stressing in the stay cable's anchorage zone was also modeled in Midas Civil. How about the loading criteria? The loading criteria as well as the loading combinations for Balang Island Bridge was defined in accordance with the Indonesian standard as KSNI T02-2005. Traffic loads such as UDL or Uniform Distributed Loads and KEL or Knife Edge Loads as well as the truck loads were modeled as moving loads. For the long span bridge, the engineer doesn't only require to perform the transitional static and dynamic analysis, but it obliges to take into consideration the particular load cases such as temperature, shrinkage, and creep of concrete, aerodynamics, earthquake, etc., which are generally representing a non-linear loading pattern. How is the construction method? Please see here a movie showing the construction method proposed for Balang Bridge. This is the pylon construction by climbing form. The pylon is 112 meters high from the top of pile cap level. You may see also here the intermediate piers. Now installation of scaffolding for pouring of pier table, formwork, and then pouring concrete of the pier table. Now temporary fixing of pier table for maintaining the stability during erection of the bridge deck. Now is installation of travelers. We start construction of the bridge deck, including installation of stay cables, segment by segment. When arriving in the position of intermediate piers, we propose a temporary fixing between the deck and intermediate piers to allow the uplift force. Final closure of the bridge deck. Then dismantling of all temporary fixities and also dismantling of scaffolding under the pier tables. Now the bridge is finished of construction. Regarding the design procedure, particularly for a long span bridge, it will usually contain at least 4 steps of analysis. First step is the initial whole bridge analysis, or what we call usually the zero deflection analysis, for obtaining the initial value of cable forces by iteration against dead loads and superimposed dead loads. The second step will analyze the construction stage in order to control the stresses, including the cable forces in each stage. The third step is to analyze the deformation for mainly the deflection control. In the fourth step, we analyze the surface state by applying all surface and transient loads. How is the construction stage analysis? In addition to the complicated loading combinations, the design of long-span bridges with segmental construction method, for example, the balanced cantilever bridge, cable stayed bridge, arch bridge, suspension bridge, etc., should seriously consider the effects of construction stages. It is not sufficient to only calculate the structure in its finished state or final state, but should also take care on the stress and deformation history occurred in every segment at every stage. In the construction stage analysis of a long span bridge by segmental method, the weight and working method of the traveler should be also well modeled. In this case, Midas Civil has a good feature to perform a comprehensive construction stage modeling. Here is the construction stage analysis in Midas Civil modeling. This is the first step to perform the pylon model and the pier tables. Then we proceed with the model of bridge deck construction by segmental modeling in accordance with the real one to be carried out in the project site. In all construction stages, we analyze the variations of cable forces, bridge deck stresses, as well as the pylon and bridge decks deformation under all construction loads, including the traveler's loads, in order to make sure that all stresses and deformations are safe in every stage of the construction process until closure of the bridge deck and installation of the superimposed dead load such as asphalt, concrete, railing, etc. This is some outputs taken from Midas Civil showing the variations of the deck stresses and the stay cables forces. This is the stage of segment number 1. This is the output of construction stage analysis after segment number 7. Segment number 14. Please see also on the variation of the stay cable forces. This is after closure and mid-span continuous pre-stressing. This is the final stresses and stay cable forces after final tuning of the cable forces to approach the design cable forces. It means in this state, the analysis of bridge construction process is completed. You may see in this stage the different variation trend of the cable forces at the position adjacent to the intermediate pier. The next step is the analysis of stresses and stay cable forces under the surface loads combination. we have to make sure that all stresses and cable forces will not exceed the allowable stresses for the permanent loading condition. Finally, this is the stay cable force variation taken from Midas Civil's output. You may see the red one as the cable forces after completion of the construction stage, and the other two variations represent the maximum and minimum cable forces under the service loads. Until this stage, the stresses and cable force analysis are now complete. Now we will check the bridge deflection. The Midas output shows this figure as the deflection under service loads combination that should not exceed the deflection limit defined by the code. Here it shows the maximum deflection of 437 millimeters that is still under the allowable deflection of 502 millimeters. Now we have to check the dynamic behavior of the completed bridge and in the construction stage. Here is the first mode as the first order symmetrical vertical bending mode with the natural frequency of 4.295 Hz. Please see the animation of model vibration of this mode. This is the sixth mode as the first order symmetrical torsion mode with the frequency of 0.663 Hz. This table shows the first 10 modes of the completed bridge vibration. On the first approximation, according to the study carried out by Zhong Matiba, the ratio between the frequency in torsion and frequency in vertical bending is equal to 2.25. Seems to be good enough. However, as it is lower than 2.5, we recommend to perform the wind tunnel test for this bridge. Now we will check the dynamic behavior of the bridge in the construction stage, especially on the longest cantilever deck stay. This is the first mode as the first order single side vertical bending mode with the natural frequency of 0.284 Hz. You may see here the animation of model vibration of this mode. This is the fourth mode as the first order single side torsion mode with the frequency of 0.65 Hz. This table shows the first 10 modes of the cantilever stage vibration. Similar to the completed bridge behavior, the ratio of the torsion mode to the vertical bending mode's frequency is slightly below 2.5. How about the wind effect on the Balang Island bridge? In many cases, the wind effect and in particular the aerodynamic behavior of a cable-supported bridge can be a dominant factor determining the bridge stability and safety, on which the influence of aerodynamic force is very important. More than for any other type of bridge, the aerodynamic stability of a cable-supported bridge can even determine the feasibility of the project. This is the static wind effect illustration. We all know how to calculate the design wind force. In case of aerodynamic wind effect, the applied wind forces are much more complicated and usually represented by drag force, lift force, and torsion force on the bridge deck, on which the three aerodynamic coefficients can be obtained through a wind tunnel test, which are depending on the wind attack angle. This figure shows an illustration on the event of aerodynamic stability that we call usually the flutter phenomenon. What is the aerodynamic instability? As we know, every bridge has its damping characteristic which can manage the stability of wind-induced vibration. This damping property is represented usually by a value of positive damping ratio. However, if the deck receives more wind attack energy that can no more be dissipated by structural damping, usually called also by negative damping effect, it can produce the combined bending and torsional oscillations due to the aerodynamic forces with rapidly increasing amplitudes and no limit until collapse of the bridge. This is an example on the effect of negative damping ratio as a function of increasing wind speed that attacks the bridge deck. The x-axis is wind speed and the y-axis is the damping ratio. In case of very high wind speed that may cause no more positive damping ratios remains working, then the vibration may be no more controllable. That may induce rapidly increasing amplitude in a combined bending and torsion until collapse of the bridge. Now how to conduct the wind tunnel test for wind-induced vibration. First, we have to define the basic wind speed that should be taken from the bridge loading standard or from the local meteorological data. In case of Balang Bridge, the basic wind speed was taken as 35 meters per second at an elevation of 10 meters high. The design wind speed can be then calculated by taking factors of deck elevation and side surface condition, so that becomes 40.39 meters per second. Then the real maximum wind speed that may occur in the project site for flutter check at surface state can be calculated by adding the safety factor and turbulence coefficient, so that becomes 60.1 meters per second. It means the bridge should have a wind resistant capacity at a wind speed higher than 60.1 meters per second. Then the section model wind tunnel test for Balang Bridge were carried out in the TJ1 boundary layer wind tunnel of the State Key Laboratory for Disaster Reduction in Civil Engineering at Tongji University in Shanghai, China. TJ1 boundary layer wind tunnel is an open circuit low speed tunnel with a test section of being 1.8 meters wide, 1.8 meters high, and 14 meters long. The fan power is 90 kilowatt and the wind speed ranges from 0.5 to 30 meters per second. This is the wind tunnel TJ1 in Tongji University. The spring suspended rigid section model was employed in the test. The section models were suspended in 8 springs from 2 testing frames installed outside the wind tunnel in order to assure the similarity of the rigidity of this model to the real bridge section. The geometric length scale of the model was determined to be 1 to 40, according to the dimensions of the prototype bridge deck cross-section, as well as the testing section of the wind tunnel and the required direct testing approach for wind-induced vibration. The model was produced in the similarity with the real bridge deck section, including the longitudinal girders and transversal beams. To diminish the influence of the 3D flow around the two ends of the section model at the test results, the length of the section model was designed to be 1.74 meters, and the gap between the model ends and the side walls of wind tunnel were about 30 millimeters. This is the control room, with the monitor indicates the testing wind speed. In a low wind speed, the vibration represents a positive damping property with decreasing amplitude and good stability. In a critical wind speed, the monitor shows a critical vibration with no decreasing amplitude. Then in a more higher wind speed, we can see a clear negative damping property showing the rapid increasing amplitude that is indicating the flutter phenomenon and the trend to failure of the tested model. Now we can see the gradually increasing amplitudes in the model's vibration. Okay, this is the graph of negative damping ratio obtained from the wind tunnel test. Considering the positive damping ratio of 1% for the concrete bridge, then we may obtain the critical wind speed as 95 meters per second. That is good because the flutter critical wind speed is highly above the site maximum wind speed of 60.1 meters per second as mentioned previously. As conclusion, first, the results of structural design analysis for Balang Island Bridge show that the design has fulfilled all safety standards required by the Indonesian Bridge Code and other international codes. Second, the results of wind tunnel tests for flutter stability show that the flutter-induced critical wind speed obtained for the surface state is 95 meters per second, with the structural damping ratio of 1% and under the wind attack angle of -3 degrees. Therefore, compared with the site maximum wind speed for flutter check, that is 60.1 meters per second, the Balang Island Bridge is proven to be stable enough against flutter for the surface state under wind attack angles between -3 degrees and +3 degrees. Third, as a long span bridge, we should take care on various design requirements. It doesn't only require to perform the traditional structural analysis at each finished state, but it obliges to also carefully consider the specific site condition so that a suitable construction method can be defined and analyzed in an optimal way of safety, cost, and timely manner. Thank you very much for your kind attention.